Hi everybody, this is project video number 3. Today we're going to talk about the vibration sensor and the magnetic reed switch. First of all, we're going to talk about the vibration sensor. We're going to select that by shorting the VIB lines on the sensor selection pin block. Looking back, this circuit should look very familiar. We've got our AC coupled output that is rid of the DC component on the left side here, and we've got our div 1 line, which contains the DC component. Now, we got our 10K ohm current limiting and protective resistor. We've got our vibration sensor. Now, internally, there are two contacts that make intermittent connection to, in this case, the ground line when the module is being shaken. So, when there's no internal connection, we'll just see 5 volts on this line. And as soon as we start to shake it, the internal connection on in the vibration sensor shorts the power here to ground. So by default we'll see 5 volts, and when we shake it, it'll short down to 0 volts ground and back and forth because the contact will make an internal switch. And we'll see this in a little while. We're going to use 2 circuits here. We're going to use a comparator. Actually, we're going to use both comparators, but what we're going to do is we're going to configure one as a buffer, and we'll get to that in just a second. I want to discuss the comparators for a second. On the comparator pin block, there are 2 pins to splice to for C1 negative, C1 positive, C2 positive, and C2 negative. And the reason for this is so that we can configure these as a buffer. Each output on the main pin block, we're only using one here, but we're using both here. CP2A and C2B. They are connected internally, and so we can actually use that as a buffer. And if you don't know what a buffer is, let me talk to you. It's another configuration of an operational amplifier. The output voltage equals the input voltage, but say we have an input voltage that can't support much current. If we overload that line, the voltage is just going to drop to 0 volts. And so what this does is it basically adds a little bit of current capability to the output. So, for instance, if we connected our div 1 line directly to our LED, we would have a series resistance of 10,000 ohms plus 390 ohms. So we might barely light that LED up on its own. It might light up, it might not. However, if we feed this div 1 line into our buffer, which we'll configure in just a minute, and then take the output and connect it to the LED line, then the LED will light up and it's no problem. We're basically using the LED as an indicator, but I also kind of wanted to teach you another configuration of the operational amplifier. So in order to configure an operational amplifier as a buffer, what we need to do is connect, in this case we're going to use a non-inverting buffer, so we're going to connect the negative, in this case C2 minus, to one of the output lines. And we're going to connect the div 1 line to the positive input. So div 1 to positive input, and we're going to connect the negative input to the output. And then we're going to connect the output, one of the output pins, to the LED pin. Now, when we actually do this experiment, we're going to connect the div 1 line directly to the LED to show you that it might light up a little bit, if at all, but as soon as we connect it to a buffer, and connect the output of the buffer to the LED, this will source more current, and we will light up our LED with no problem. I'll also shake it so you can actually see the LED going on and off. Actually, let's do that right now before we get to our second circuit. The first thing you're going to want to do is take your 2-pin header and short the VIB pins, the VIB pins, on the sensor selection pin block. Next, plug in your AC adapter. Now, if I connect the div 1 pin to the LED pin, as we discussed, we'll have a series resistance between the 5 volt line and the LED of 10,390 ohms. So we might see the LED light up barely when we shake it. So as you can see, it's barely lighting up when we hit the sensor. So let's connect our div 1 pin to the positive input of our comparator 2, and we'll connect the negative input of comparator 2 to one of the outputs, and we'll connect the other one of the secondary output to the LED, as discussed in the schematic. So basically, by adding our buffer, we've made a current amplifier. The signal going to the vibration sensor is the same voltage, but we don't get a voltage drop because we can actually source enough current to properly light the LED. So the series resistance of the output of the comparator is through the 390 ohm current limiting resistor on the LED line. So let's go back and talk about another circuit. As you can see, I've disconnected the output of the comparator to the LED so we can use that for our secondary circuit. We'll leave those connections as they are, and we'll use the AC coupled output this time. So for this, we'll get a little bit of a stronger signal on the AC coupled output because we do get a 0 to 5 volt ringing when we shake the device. So we'll get a little bit of a stronger signal, AC coupled signal on the AC line. So what if we connect our AC pin to the C1 plus pin on the comparator pin block? The AC pin is on the main pin block, and we connect our variable resistor pin, the VAR pin on the main pin block, to the negative input of the first comparator. Now, we can use this to tune our sensitivity because with our variable resistor, we can tune the voltage to anywhere between 0 volts and 5 volts. So basically, the output will by default be 0 volts, low, because we've got a negative voltage consistently on the negative pin. And we know comparators, when there's more voltage on the positive pin than there is on the negative, the output is high, 5 volts. When there's more voltage on the negative pin than there is on the positive pin, the output is low, ground. In any case, we can use this to tune for high sensitivity or low sensitivity. If we turn the variable resistor, the VAR variable resistor, clockwise, we bring the voltage up, closer to 5 volts. If we turn it counterclockwise, we bring the voltage down, closer to ground, but we can tune anywhere in between. So what we're going to do is we're simply going to connect the AC pin to the C1 plus pin, the VAR pin to the C1 minus pin, and we're going to connect the CP1A, the output on the main pin block, to the LED, and we're going to calibrate for sensitivity. We've still got our vibration sensor selected on the sensor selection pin block, and as talked about previously, we're going to take the VAR pin on the main pin block and connect it to the C1 minus input on the comparator pin block. We're also going to take the AC pin from the main pin block and connect it to the positive input of the first comparator. Then we'll take the CP1A output. Sorry about this, I need to see where I'm going here. Sorry. There we go, and connect it to the LED. So it's detecting vibration, me moving it around. I can shake it, and it'll calm down. So the VAR resistor, or the variable resistor right here, I can tune it using a small flathead screwdriver, if I can actually get it in there. In the words of RoboCop, I'm having trouble. So I'm lessening sensitivity by turning it clockwise. I'm hitting the board pretty hard. Sorry. So now it's on its lowest sensitivity. And if I bring it all the way right, you just turn it a whole bunch of times. It's more sensitive now. And as I bring the voltage on the VAR line closer to 0 volts, then every time I hit the board, the threshold on the comparator is lower, so the output will go high. There we go, nice and sensitive. So I'm just going to put the board down and I'm just going to barely touch the table, and you can see it. So this is the vibration sensor right here, and you can actually hear when you shake it. There's a little ringing. That's the sounds of the contacts internally making the connection to ground, as talked about in the first schematic. So I barely moved this thing, and there we go. Now what if we took the output of the comparator and connected it to our in pin on our monostable multi-vibrator? We didn't talk about that in the schematic, but if you've been following along with the project videos, that should make sense. So what we're going to do is we're going to connect and basically create a voltage or signal widener. So let's take the DLY output. Sorry if you can't see what's going on. Lots of connections on here now. And we'll connect that to the LED. Now I'm knocking on the table. Single pulses. And of course you can tune the length of that pulse by turning the DLY potentiometer right here. Turn it clockwise to make the length of the pulse width longer, and counterclockwise to make it shorter. So there you go. So I'll show you the connections that I made for both circuits minus the LED, because we're using two circuits here, and you should know basically which outputs we're connecting to the LED. I will include the connection made for the monostable multivibrator for the second circuit. The connections from the first of the two vibration sensor circuits are outlined in red. The CP2A output is circled in red, as we would have connected that to the LED, but the secondary circuit is outlined in green and in blue. The output CP1A is circled in blue as well, but we went a little bit further and connected that to the input of the 555 timer, and the output, the DLY output on the main pin block, is connected to the LED. The VAR1 and the DLY, the VAR1 and the DLY potentiometers, variable resistors, are circled in blue, as we use those in the second circuit. Time to talk about the magnetic reed switch. So the first thing we're going to want to do is we're going to want to select the mag pins by shorting them on the sensor selection pin block. And what this is, it's just a switch when it's normally open, which means that there's no connection being made. When it senses a magnetic field, the internal switch closes and connects to ground. So by default, no magnet anywhere near the sensor. We just get 5 volts at the div1 line. It's just a steady 5 volts. So the output right here is normally high. And when you bring a magnet close to the magnetic reed switch, the internal contacts make connection and it pulls that signal to ground. It basically shorts the line here to ground. Now we've got a 10 k ohm protective resistor here, so that's safe. So no magnetism, magnetism detected. No magnetism detected. And we're going to use a similar circuit, a similar buffer circuit, as we did in the first part of the video, by connecting the div1 line to the C2 minus pin. See, since this is normally high, we're going to want to invert the output. So we're connecting positive to the negative. And we're going to connect one of our two C2 plus pins, to one of the two output pins, say C2B. And we'll take the output, connect it to our LED. So just to remind you, this is a buffer. The output is actually an inversion, it's an inverting buffer. The output is opposite of what the input is, but we still get that current amplification to drive that LED. So if we didn't have this, we'd have, by default, if we connected the div1 line to the LED, we'd have a very faint on LED, because we'd have a series resistance of 10K plus 390 ohms, which will barely power the LED as well. It would always be on until you actually brought a magnet close to the reed switch. So what we're doing is we're connecting that normally high output to the negative input, so we're inverting the logic. The negative input of this buffer, connecting the C2 positive to the output, and as well our secondary pin of the output to the LED, and that'll invert it. So by default, this LED should be off. We put a magnet in front of the magnetic reed switch, and that LED will turn on. So let's give that a try. I've made the connections, which I'll show you in just a minute, and this is the magnetic reed switch right here. So we've inverted the logic, and here is a magnet that will be included, and I'll bring it close to the magnetic reed switch. So this circuit added current amplification, and we inverted the direct output of our div 1 line. Now if we decided to heck with this circuit, let's just connect the div 1 output as is directly to the LED. This is what we'll find. A dimly lit LED. Again, I put my magnet close to it. On off, but it's a dimly lit LED because we've got a series resistance of 10,390 ohms. So, not advisable. But you could take your div 1 output as a normally high output and connect to your Arduino if you so wish. So let's talk about one more circuit, and then we'll end the video. In the case of the AC coupled output, we have no DC here. We should see 0 volts by default. And when you bring a magnet close to this, depending on how fast you do it, you might see a couple spikes at the AC output. Even if you hold the magnet there, you'll see a couple spikes and then you'll see 0 volts again, because it's detecting a change on the line. So, because of bounce, it is a switch. When you bring a magnet close to it, it might toggle the switch a couple times internally over a very quick time period, a couple milliseconds perhaps. In any case, we can use those spikes with a comparator, and we can even filter out some of the smaller spikes by using a variable resistor. So we'll connect our VAR pin to the negative input excuse me, of our first comparator, comparator number 1, C1 minus. We'll connect our AC output to our positive pin of the first comparator. And so we'll set sensitivity with the variable resistor. We'll basically have a constant voltage on our negative input, and when the voltage of these spikes surpasses the voltage of the negative, the output will go from 0 to 5 volts, perhaps a couple times. But we're going to connect that output to our 555 timer in monostable mode to turn those couple spikes into this, a single spike. Now, I haven't put the 555 timer circuit on the board, but we've covered it in many of the other project videos and certainly in the product videos. So by now you should know that the 3 elements associated with the 555 timer are the DLY variable resistor to determine pulse width, the in pin, which we would connect to our CP1A, and our DLY output, which we'll connect to our LED. In this case, just just to test out our circuit first of all, before we connect to the 555 timer, we'll connect our CP1A directly from the output to the LED to see if we can actually see these spikes on our LED. I have not tuned the variable resistor, VAR. I'm seriously just taking the magnet, and as I bring it close to the reed switch, I bring it in. You see the LED light up? As I pull away, you should see the LED light up for a split second too. That on-off is the reed switch closing and opening, and those are the coupled spikes across the AC coupled output that's being essentially brought to 5 volts by our comparator. I'll do it a couple more times. Now, what am I going to do with this, you might ask? Say I want to make a circuit that once it detects a magnetic pulse, you don't want to keep it on for a certain period of time. You just want that to trigger another function in a microcontroller or in another circuit you might have. So it would detect that quick spike when you bring it forth and pull it away. Now we can take that output right here from the comparator 1, tie it to the in pin on the 555 timer. I know you probably can't see what I'm doing right now, but I'll show you the schematic or the pin out in just a moment. And I'll connect the DLY output to our LED. Normally off, I bring the magnet close to the magnetic reed switch, and we have a pulse again. I can change the pulse again with the by changing the resistance on the DOY potentiometer. Turning clockwise will make the pulse longer. Counterclockwise will bring the pulse shorter. And of course, we can tune sensitivity by turning the VAR potentiometer. Clockwise will make the sensitivity lower. Counterclockwise will make it much higher. So I hope you've learned a little bit in this video. We're getting a little bit more into different configurations of the operational amplifier. So far we've covered the comparator, the buffer, the non-inverting buffer, and the non-inverting amplifier. So thanks for watching. Next we'll cover the relay attachment and the PIR attachment, the motion detector attachment.
The connections from the first circuit we explored with the magnetic reed switch are in red. The CP2A output is circled in red because you can put that to the LED, but we actually concentrated more here with the connections for the second circuit, which are in blue. And the output, the DLY output on the main pin block from the 555 timer goes to the LED in this case. I've circled the VAR1 variable resistor and the DLY variable resistor in blue, as those are the two variable resistors that we would have used in the second circuit.